Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to show you how the x1 functor that we defined using projective resolutions can be used to answer the extension problem. And the way I'll do this is I want to introduce a more precise way of looking at the extension problem by considering the Yoneda Ext. So what is this Yoneda Ext functor? Okay, so we're going to start with the same type of data that we did for the x1 functor. So we'll start with some ring R, and we're going to pick two modules over that ring, say M and N. And what is this Ext of Mn? That's the functor that we want to define. It's going to be a functor in both M and N. Okay, it's going to be the set of equivalence classes of short exact sequences. Just look at this blue line here. Here's a short exact sequence, 0 from n to e to m to 0. Okay, so I'll denote this short exact sequence with this eta here. So note the n is fixed. It's on the right hand side here, but it's on the left here, so it's going to be the sub-module, so to speak, here, and the quotient is going to be the m here, and here is whatever fits in the middle. Okay, so you can have all sorts of such short exact sequences, and what we want to do is we want to look at equivalence classes of them. So we have to say when are two such short exact sequences equivalent. So let's suppose we have another such short exact sequence, eta prime, 0 to n to e prime to m. Okay, so when is this eta prime equivalent to this eta? Well, the definition is that these are equivalent. Eta is equivalent to eta prime if and only if we can make a commutative diagram between these two short exact sequences in the following manner. Okay, so basically the commutative diagram will have identity maps here, so I'll replace them with an equal sign here and an identity map here, and there's going to be some map from this e to this e prime, and this map, if it happens to be defined in such a way that these two squares commute, it will have to be actually an isomorphism. Okay, so this actually does define for you an equivalence relation. And a nice sort of exercise to see in this is that, well, one type of short exact sequence that you get, which is actually quite distinguished, is when you just take for E here, just the direct sum of N and M. And in that case, you can have a projection onto this M here, and also an inclusion of N into the summand, which is N. Okay, so that's a rather distinguished element inside there, and it's not difficult to see that all the things which are equivalent to that are also going to be essentially the split sequences. Okay, so if you have a split short exact sequence, okay, they're the ones which are equivalent to the direct sum of n and m being put here, and that's the projection, and that's the usual inclusion. Okay, so there's a distinguished element inside this set. So this is the set, and we want to study this set. Okay, what are the elements of this set? And one of the ways to study this is to observe that maybe you want to study this for all m and n at the same time, and in fact we'll do that, and we'll see that this is actually functorial in m and n. As a functor in n, it's going to be covariant. As a functor in m, though, it's going to be contravariant. And this is exactly the type of behavior that you see, functorial behavior that you'll see of the x1 functor. Okay, so it precisely mimics that. So you might be interested to know, well, in what sense is it functorial? Okay, so let me just show you how that works. So suppose you have two R modules, not just n, but also n prime. Okay, so you can look at Ext of Mn and also Ext of Mn prime. So if you have an R linear map from n to n prime, you should have a map Ext mf from Ext mn to Ext mn prime. Okay, and so that will take you a short exact sequence like the one you see here, this blue one, which I've rewritten here, to a short exact sequence, but here, though you end with an m over here, you have to start with an n prime over here. Okay, and the data that you do have is you have a map from f from n to n prime. So we need to have some sort of short exact sequence. This is going to be this one here, eta prime, that has as a submodule, so to speak, n prime, and the quotient is going to be m. And the question is, how do we define that? Okay, so we need something that's inside here. and we'll call that E prime. And it needs to fit in like this. That's what we're going to do. We need to define this, and actually we'll make it by fitting in this. And the way we'll do this is we're going to use the notion of a push-out square. Here you have this map here and this map here. You have a push-out square which goes like this. And that will map to here and make this whole diagram commute as well. So the notation for the push-out square is, I guess, so sometimes you put in a little square like that. The way you define it is quite simple. What this push-out square is, essentially the notation will be you have E and then it's a coproduct n prime, and then that's over this n. So what does that mean? Well, firstly, the coproduct you start off with is just the direct sum of E and n prime. So that's the first thing that you do. And of course you have maps from E to E direct sum n prime and n prime to here. But if you just use those maps and just use this, you'll find that this diagram doesn't commute. Where n goes to won't end up the same if you go around this way, where you'll always land in the first component as when you land in the second component. So what we're going to do is we're going to equate the two ways you go around by modding out by the image of minus iota, where you go that way, to f. Okay, so let's just see what happens and see how this square commutes now if you make this the push-out square. Okay, so this is going to be the coproduct. Okay, so here we have the direct sum modulo this image here. Now, of course, you have E maps to this direct sum, so it also maps to this quotient, and similar with n prime in the natural way. And what we want to do is we want to check that indeed when you go around this way and this way, you get the same answer. Okay, so let's just do that briefly. So if you go around one way, you have iota of, say, n, and then you slot into the first position, iota of n, comma 0. If you go around the other way, you'll have f of n, and you slot that into the second position, 0, comma f of n. And the point is that these two are going to be the same inside this quotient, because I guess if you subtract this from here, you'll get minus iota n, comma f of n, and that's inside the image of this minus iota f. Okay, so that makes this square commute. I guess the next thing that you need to do is to see, well, what are the maps here? Okay, so what's this map here? Well, this is the direct sum. And I guess the only thing that you have to check is that you can map from here to here. Okay, so what's that map? So I guess you can map E to M. So it's clear how that goes. And then you also want to map n prime, okay, which came from here, has to go to 0. So that has to go to 0. And then it's just a matter of checking that actually, if you make that definition, okay, it does induce a map from this quotient to M. Okay, so I won't go through why that's true, but you can check that quite easily, that that is indeed going to be the case, and you have this map here. So I guess the last thing that you need to do is just to check that this is a short exact sequence. And so I guess the main thing to see is, well, firstly, you know that E surjects onto M. So it's certainly the case that this surjects onto M, since this maps this E component here onto M the same way this one does. So that's going to be surjective. So you just need to check what is the kernel of this map here. And so how do you get things in the kernel? So to get things in the kernel, I guess you need first realize that all of n prime in the second slot will go to 0. So that's all in there. And the other things that you'll get in there are the things that come from E, okay, in that first slot, okay? And which things go to 0 from E? Okay, they're the ones which are in the image of this iota, in the image of this iota. And of course, if you're in that image of that iota, comma 0, you can shift that over to the other side in this quotient. So really everything just comes from n prime. So the kernel is just n prime. Okay, so that's roughly why it's true. You can go through slowly in your own time and check that this is indeed a short exact sequence. And not only do you have a short exact sequence like this, but you actually have a morphism of these short exact sequences, which is rather nice and allows you to relate these two extensions. Okay, so that's how you get functoriality in the n here. Of course, maybe instead you want to look at morphisms in the contravariant variable g from m to m prime. Okay. Well, in that case there, you can also do something similar, but now you'll need to look at the notion of a pullback square. Okay, so that's something that's a little bit, that's dual to this notion of a pushout square. But I'll let you have a think about what that involves. Basically, what you want to do is you want to dualize the type of notion that you see here. So this direct sum becomes direct product. And instead of looking at an appropriate quotient, which makes sure that some square commutes, you look at the appropriate sub-object, okay, that makes sure that the square commutes. Okay, but other than that, it's the same sort of deal. Okay, now at the moment, this is just a functor. This x is a functor which maps into sets. Of course, the x1 is extra nice because actually it maps into abelian groups. It turns out, I won't go through this, but it turns out that actually that this Ext functor also has a structure of an abelian group. And it's not too difficult to define. I just won't write it down here, but the basic idea is if you're given two extensions, okay, maybe like this eta and this eta prime, you can just take the direct sum of those two extensions. And that will give you an extension of m direct sum m by n direct sum n. So unfortunately, it's not an extension of m by n, but an extension of m direct sum m by n direct sum n. So the main thing is, how do you take that extension and to bring that down to an extension of m by n? Well, we can use functoriality, okay? So there's a, I guess, maps from, for example, n direct sum n can map to n. You just add elements of n together. So n direct sum n maps to n. Okay, so you can push that down to something inside n. And then similarly, there's a diagonal map of m into m direct sum m. Okay, and then you can use that. And that will give you your addition inside this Ext. So the theorem I want to present to you is, well, how do you study this Ext functor, right? So it seems to be completely abstractly given, and is there a way of actually computing what this is? And it turns out that, in fact, it's essentially just the x1 functor. Okay, so that's the theorem here. Okay, there are functorial isomorphisms from x to mn to x1 Rmn. And I don't want to prove it fully, but I want to show you basically what the definition of this phi is so that you can see why it ought to be true. Okay, so it's a wonderful sort of a result, and it's typical of the types of things that you might want to do in homological algebra. Okay, so of course, if you want to compute what is this x1, there's a couple of ways you can do that. You can use an injective resolution of n or projective resolution of m. So we'll use a projective resolution of m. Okay, so that's going to be p dot maps to m. So here it is in the first row here, m. So you've got p2 maps to p1 maps to p0 maps to m, and of course it could go back, but we'll only need this part of that projective resolution. Okay, so suppose we want to, for example, define what is phi. Okay, and so what I'm going to do is I'm going to consider some extension eta inside here. So this eta is going to be given by this second row here. Okay, 0 maps to n maps to e maps to m. Okay, so this is an exact sequence. And one of the things that we've seen is that if you have a map on modules, so in this case here, it's just the identity map from m to m. Okay, and you have a resolution of this, just any old resolution, so to speak, so just some acyclic or some exact sequence which ends in m. And if you have a projective complex which maps into this m onto this m, okay, then you can actually lift this one here to a chain map, and that lift is unique up to homotopy. Okay, so here's the chain map, that's the blue lines here, F2, F1, F0, okay, and homotopies are these purple diagonal lines coming back like that. Okay, so that's something that we have. Okay, so if we're given this eta, okay, and we pick this projective resolution, we can get some of this, you can get this data, okay, of these blue lines, and it's essentially unique up to this homotopy. Okay, so let's interpret this in terms of the complex that we use to compute this x1 Rmn. Okay, so let's look at that computation. So what do? To look at that x1 Rmn, we replace this m with this projective resolution part, and we look at the homomorphisms of that into n. So we do the homomorphisms into n, so that's going to be contravariant. So we start with this p0 maps to n, then p1 maps to n, then p2 maps to n. Okay. So in this chain map, of course, you have a map from p1 to n. So that's my f1. So this is inside here, hom r p1 maps to n. Okay, so that's very good. So the next thing that we note is that, well, what happens if we look at the image inside here? So where does that map to? So remember, we have to use the differentials here. So we do this one and then this one. So going around this way is the same as going around this way. And going around this way goes through the 0, so it's got to be the 0. So what you'll find here, in fact, is that since you're going to 0 over here, that this is a cycle. Okay. So remember, what is x1 Rmn? To remind you, it's going to be the kernel of this map modulo the image of this one here. Kernel of this one modulo the image of this one here. The kernel of this map, they're the cycles, and the image are the boundaries. So it's the cycles modulo boundaries. So we've got a cycle here, f1. That's rather nice. This gives us a cycle. So that already seems to suggest that we're going to get something inside here. Of course, we can modify this thing. And what is the type of thing that you can modify it with? Well, it's going to be some sort of homotopy. But if you look at this exact sequence here, this complex here, remember there's lots of zeros. So the data of this homotopy is actually very limited. Most of the maps have to be 0 because you're mapping to 0. The only one that really matters is this S0. So let's just put this S0 in. And if we're going to say this is F1 modulo homotopy, that means that you can change this F1 by a homotopy. So essentially you can add what happens when you go around and like this. Okay. Now this one's 0, so basically you're just adding in what happens when you go around like this, which is just the image of this. So basically this maps over to the other side. And you can change it by whatever homotopy that you like. Okay. So, so yes, it turns out that in this case, what you'll see is essentially the data that's presented here is precisely a cycle up to this homotopy, which means up to this boundary. You're given a unique cycle up to this boundary. So we're really given by this theory here a cycle modulo boundary, which identifies a homology class, which call phi of eta, which is in x1 Rmn. And that's how you arrive at the definition of this map phi, where if you have some sort of extension of m by n, okay, so such short exact sequence here, okay, you get an element here. Okay, so I guess the only thing that we need to do now is to find the inverse, okay, to show that this is an isomorphism. And I'll just define for you, I'll show you how you can define this inverse, because this is very nice as well. Okay, so let's try to define the inverse, and let's just see how that works. So basically now we're going to have an element inside here, which is something like this. It's going to be a cycle here, so an element of hom rp1n, which maps to 0, modulo something here. Okay. So how do we define this phi inverse? So the first thing I want to do is I want to sort of reduce the information here and just look at essentially the first part of the projective resolution. So remember, when we construct this, normally what happens is that we have a surjection from P0 to M, where P0 is projective, and we look at the kernel, and I'm calling that kernel K. So that's the kernel of D0 here. Kernel of D0, of course, is equal to the image of P1. And what's the image of P1 by the first isomorphism theorem? Is the image of P1 is P1 modulo the kernel of D1, which is the image of this. So that's P1 modulo D2 of P2. Okay, so that's the first thing to note, is that's what we have for this kernel here. Okay, so we're going to basically get a shorter exact sequence by replacing this P1 with K. That's the kernel of P0 to M. So you will have this short exact sequence 0 to K to P0 to M to 0. So this is an extension of M by K, and what I kind of claim is that this is, in some sense, a universal extension of things by M. Every other extension of M by something comes from this, okay? In fact, it comes from it by functoriality, and I'll show you how, okay, in a moment, okay? So let's just see what's going on. We're going to start with some sort of element F1 inside hom RP1N that goes to 0. It's a cycle, okay? So we're going to be given a cycle like that. So what's being a cycle mean? So being a cycle, remember how that works. So you've got to map from here to here. Okay, now you want to map from P2 to N. Okay, that's by composing this. So F1 composed with D2 is equal to 0. Okay, so it's a map from P1 to N, but it's going to be 0 on D2 of P2. So that means that this map F1 rather, from P1 to N, will factor through this quotient P1 mod D2 P2, which is isomorphic to K. So really you have an induced map F1 bar from K to N. So we've taken this short exact sequence now, which ends in M, but it starts with K. And we have this map K to N, which is F1 bar. And what we want to do is we want to define from this element of x1rmn, which is this cycle, okay, an extension. So we've got this map here, okay, and we've got this short exact sequence here, okay, so that's an extension M by K. So what we do is we just use functoriality by this F1 bar to get you a short exact sequence giving an extension of M by N. So basically we just use the pushout square here, P0 coproducted N over K, okay, have this pushout square, and this is going to give you the inverse of this homology class. And that's how you define the inverse to this functor phi. And so this is a very, very lovely illustration of some of the things that you can do with homological algebra. In this case here, this x1rmn actually in some sense solves the extension problem, in the sense that it gives you a description of what this functor is. Okay, so you have this completely as a set, and in fact it gives you extra structure on this set. It's got some additive group structure on it. And the other thing that's rather nice about it is that if you want to check that something is split, of course, you just check that something is 0 inside there. Okay, so that x1 functor really tells you, okay, when that's going to happen. Okay, so it gives you an obstruction to being split. And this, by the way, is fairly typical of the type of phenomena that you see with homological algebra. You introduce these derived functors, and for the most part, these derived functors are usually just tools, they're abstract tools used to study the original functor that you're interested in. Okay, so for example, if you're interested in the hom functor, okay, you need to just look at Ext functors. But it also turns out that usually for small values, okay, so for the first few derived functors, it's often the case that there are interesting interpretations of them as well. Okay, and in this particular case, we'll find that x1 actually, you know, so hom, of course, that's telling you the homomorphisms from M to N. That has a very simple interpretation in terms of modules. When you write down this x1rmn, because it involves choosing projective resolutions of the M or injective resolutions of the N, if you just go by the definition, it looks like there's no natural sort of interpretation of what it is in terms of the modules themselves, okay? It looks like that they're just tools really to study hom. But in fact, often it's the case that you can find some reinterpretation of that group, okay, or whatever that functor is, in terms of the original objects. So in this case here, you see when we define this Yoneda Ext functor, okay, it's just using the module category. There's no choices involved at all. And that's one of the things that's rather interesting about homological algebra. I hope you enjoyed this adventure in pure mathematics.